Alright, I'm going to record this video slightly differently so you won't see my beautiful face as I'm making the video, so I apologize for that in advance. So we're going to try this out, see how it goes. It's a little bit quicker logistically for me to do it this way, so here we are. Let's get started. We are going to finish up section 4 today, or that makes it sound like there isn't much left. We are going to do the second half of section 4 today. So let's get started. So this is 6.4, continued. So here we go. Should probably hit this one time. All right. So what we're going to do today is apply the fundamental theorem of calculus. I'm assuming you watched part 1. We said a few things right at the end of part 1 that were really important. Specifically, every continuous function is a derivative of some other function. Every continuous function has an antiderivative, and integration and differentiation are inverses of each other. So hopefully you've got that written down somewhere in your notes. What we're going to do now is apply some of this stuff from the fundamental theorem of calculus. So, for instance, let's take and find the derivative of this function, negative pi to x, of cosine t dt. Right? Well, remember that we learned in the previous video that the derivative and the integral are inverses of each other. And since this is an area function, when we derive this, we will just end up with cosine of x. Okay? In this situation, f of t is cosine of t. So another example. Now, because these functions are area functions, the chain rule is going to apply. Okay, so if I give you the function y equals the integral from 1 to x squared, cosine of t dt, then when I derive this, the outside piece will be the integral function, and then at the end of it, I will have to multiply by the derivative of the inside, which is x squared. So let me show you what I mean here. To find dy dx, find dy dx, what I'm going to do is obviously take the derivative of this, so I guess I just write this d dx on both sides here. So I will take the derivative of the outside, which will result in cosine of x squared. But then I have to times by the derivative of the inside, which was x squared, so I'm going to multiply by 2x. Right? So that's going to end up being the derivative. So the only thing that's different about these is that you have to remember to derive by the inside. And I would claim that we always are, we just never actually go through the motions, because the derivative of x is 1. So if you multiply cosine of x times 1, you get 1. Right? So that is sort of a special case there. I should also note that it doesn't matter what the lower bound is as long as it's a constant. If it's a constant, then the lower bound doesn't matter. You don't have to worry about it. It's built for any a. Okay. So I think that's probably enough of those. So let's go with the same instructions here. If the function is presented in this way, y equals the integral from x to 5, 3t sine of t, for example, dt. Then you have to put it in standard form before you take the derivative. So y would be the negative of 5 to x. Notice we put the constant in the denominator, 3t sine t dt. Okay. So then if I want dy dx, let's write it to the side here. Dy dx will be equal to negative 3x sine of x. Okay? Make sure. Yeah, we're going to get there. All right, last situation that can show up here where with these area functions is if you get something like where we put a variable into the lower and the upper bound. So if you had a function that was y equals the integral from 2x to x squared. In this case, what we're going to do is we're going to break this up into two integrals. All right, so, well, I guess I should give you the integrand. 1 over 2 plus e to the t dt is inside of the integral here, okay? So we're going to break this up into two integrals, and let me show you how we're going to do that. Ultimately, we're going to take the derivative of it, and here's what we're going to derive. It's going to be the integral from 0 to x squared of 1 over 2 plus e to the t dt minus the integral of 0 to 2x of 1 over 2 plus e to the t dt. Okay? And so from there, then you can take the derivative of each one. What you'll end up with is 1 over 2 plus e to the x squared times the derivative of x squared, which is 2x, minus 1 over 2 plus e to the 2x times the derivative of 2x, which is 2. And you can put those each in the numerator. We're not going to spend a lot of time on why this works. Just remember that what you're doing is you're going to take 0 to the upper bound of the integral minus 0 to the lower bound of the integral and then compute it that way. It's such an uncommon thing that it's maybe not even worth spending time explaining it, but it does show up occasionally, and that's how you handle it. The geometric or graphical understanding of what's going on there is not really worth our time, but if you are curious about it, we can certainly talk about it in class. Okay, so let's go on here. So that's an application of this fact that derivatives and integrals are inverses of each other. Now, let's do a different type of example. Let's do the type of example where we're given a function. So find the function y equals f of x with derivative dy dx equals tangent of x. Now, notice here, we are not trying to derive this. Deriving tangent's not that hard. Anti-deriving tangent, though, pretty difficult. In fact, it's not something that we know how to anti-derive, and you could work on it for a while. You could try u substitution. You'll see that it's actually quite difficult. You could put in Wolfram alpha or look it up in an integral table or something. It's been found out, right? But it's not one that we have memorized or have to memorize. So the way that we're going to find the way that we're going to anti-derive this, in other words, find the function whose derivative is this, is we are going to use an area function. One other bit of information, this has to satisfy f of 3 equals 5. Okay, so let's set up this area function. It's going to be this. F of x is equal to the integral from, now the lower bound here doesn't matter. The lower bound we're going to leave blank for right now. We're going to go up to x. And then inside the integrand, what we're going to do is we're going to put tangent of t dt. Okay? Now let's deal with the lower bound. You should pause right here and see if you can figure out what the lower bound has to be. The other thing is, in fact, let's do this. Let's write it out like this. So I'm going to put a down here as if we didn't know the lower bound, and plus c, because again we're anti-deriving, right? The goal here would be to derive this and get back to tangent of x, and I think that will work. If I take the derivative of this integral function, I'll get tangent of x. Derivative of c, any constant, is 0, so I will get back to this. Now, I also have an initial condition. I'm told that f of 3 is 5, so I need to finish up this function, taking that into account. So when I plug in 3 into this function, when I plug in 3 to the upper bound, I need to get 5 out the other side. All right, so that tells me that my lower bound has to be 3, tangent of t dt, and then my c is going to be 5. And then if you don't believe me, check. Let's find f of 3. F of 3 would be equal to the integral from 3 to 3 of tangent of t dt plus 5. Well, the integral from 3 to 3 of tangent of t, the integral of 3 to 3 of anything is 0. So this equals 0 plus 5, well, that just equals 5. So we have that f of 3 is equal to 5. Right, so that satisfies the initial condition. Okay, so now I'm thinking that we should do another one of those. Let's do one more of those and we'll call it good. So you should try this one on your own and see how it goes. We want to have the same instructions. We're trying to find the function, and we're given that dy dx is equal to the natural log of sine of x plus 5. Okay? So what we want is, and then, back up a second. The initial condition is f of 2 equals 3. Okay, that's our initial condition. So just to reiterate, trying to antiderive this would be impossible, nearly impossible. Like I said, you could use Wolfram alpha or something, probably could generate the antiderivative. But for our purposes, it's basically impossible to do in the standard format that we learned in the fall. So what we're going to do is we're going to use an area function to get the function whose derivative is natural log of sine x plus 5. So it'll look like this. Again, you should pause and see if you can come up with it. It's going to look like this. Y equals the integral. Upper bound will be x. Inside is going to be natural log of sine of t plus 5 dt. And then we just need to set the lower bound in the plus c. The plus c is going to be 3, and the lower bound will be 2. And again, you can always check. If you plug in 2, you'll get 0 plus 3. So you will get that y equals 3 when x equals 2. Plug in 2, you get 0 plus 3. You get 3 out for y. All right, and I think that pretty much wraps up the important stuff, the important applications of the fundamental theorem of calculus. So just to reiterate, integration and differentiation are inverses of each other. They undo each other. We showed that with the first set of examples. And then every function, every continuous function is a derivative of some other function. And so here we're given a derivative. And you might ask, well, what function is that a derivative of? It's this function right here, this area function. So, excuse me. So you can be mad that it's an area function and it doesn't look like a traditional function, kind of like a piecewise function. Excuse me. But it's a perfectly legitimate function. We could plot points, and we could get a sketch of the graph of what it looks like. So it's a perfectly acceptable function. It's an area function, and it's another way to find an antiderivative given the derivative. And I think that pretty much wraps up section 4.